Hello guys, this is Farhan from AlgosFromScratch, and I welcome all of you to this amazing YouTube playlist on building DistilBERT model from scratch using PyTorch. This is going to be the 8th video of this playlist, and in this specific video we are going to start working on the encoder part. So in our previous videos we covered the embedding layer. We also developed a naive classifier where we just got the values from the embedding layer. We passed it to the classifier head without passing through the encoder layer, okay? And I mentioned over there that we are going to add these encoder parts in between these two layers now. So this is going to be the start of the encoder part. So this, if you remember, this is the multi-head attention part inside the transformer block. This is the very first block that we see, okay? And inside this we have these multiple heads, like head 0 to head 11 in case of the DistilBERT model, okay? So inside each head we have a mechanism that is called self-attention. That self-attention is the heart of the transformers, okay? It tells the model about the contextual meaning of the tokens in a sequence or in input, okay? So first we are going to start with the single head, where we will be just creating a single head to get the contextual meaning, okay? We'll understand that single head, and then in the next video we will just split the single head into multiple heads, okay? So this I will start with a single head and I'll perform some steps in it. So if I just come here in this notebook, okay, so before starting this, if you open this this attention is all you need research paper, okay, and come down here, you can see here this is the complete architecture, okay, that we are working on. So we built this input embeddings, okay, and then this positional encoding part as well. Then we added a classification head after this block. Now we are going to start building this block, okay? And in this block, if you come down here, we have this attention, okay? We call it the scaled dot product attention, okay? And here is the part that I was talking about. This is the single head, okay, and this is the multiple heads, okay? So if you look into this multiple head, you can see scaled dot product attention, the same architecture here, but you can see there are multiple, you can see dimensions or layers in it, okay? So these are the heads, okay? So we are going to develop this part now, the scaled dot product attention. And once we are done with this, we will then convert it to this, okay? I will then show you the difference between these two, okay? So in order to do this, we are going to implement this formula, that is the softmax q k transpose, and divide the whole term with the dimension of k, and then this multiplication with the value vector, okay? So you can see here we have these three vectors, q, k, v, and in this q, k, v, we use basically all these q, k, v in this formula, okay? And this softmax function as well. So this is the complete architecture that we are going to build in this specific video. So I'll quickly switch to the coding screen over here, and first of all I'll just start with the class, okay? So let's call it attention head class, okay? I'll just inherit it from nn.module, and then here let's start with the constructor. Okay, in this constructor, what I need, first of all, if I just come here, I will need to create these QKV, and these QKV will be having the same dimensions, like 7, 6, 8, the same dimension of our input embeddings. Okay, so for that, the important parameter that I will be uh, passing here is the dimension, and dimension is going to be equal to model uh, config. So we already have this in the model config dictionary. Okay, and from this I will be just extracting the dimension. Okay, once I get this dimension, I can then, okay, here I'll simply call the parent constructor. Okay, and yeah, oh sorry. Okay, so here now, first of all, self dot, I'll be creating these 3 projections. Okay, so I I'll quickly call them Q linear. Okay, just like we saw in the original model. Okay, then it is going to be equal to nn dot linear. Okay, and it is going to have the dimension in and a dimension out. Okay, then we have, okay, so I'll just copy these and paste them. Okay, and the next thing is we have this k linear layer and this linear layer. Okay, and yep, nothing else. Okay, so yeah, that is it. Now in the forward, okay, so I'll just quickly check this. Okay, now we will be creating QKV from this, and softmax we already have. So I think that is all we need for the constructor. Okay, and now let's start with the forward function. This forward function now is going to get, first of all, the itself, and then it will ask for the input embeddings from the embedding layer. So we can say that input embeddings. Okay, and after this we also going to need the attention mask here. Okay, so if I show you this, you can see we have this M mask optional, but we are going to use it, so definitely then we are going to get this in the forward. Okay, so I will just quickly add it here, attention mask. Okay, and yeah, that is all. Now I'll quickly just create these QKV. Okay, and let me just check these suggestions. So yes, they are correct. So I'm just going to call the Q linear, K linear, and V linear, and I'll pass the input embeddings. So yeah, so what these QKV are going to get. Okay, so if I show you them right here, so we have, let's say, from the input embedding layer, if you notice here, this input embedding, we have, you can see we have this 2 1 to 8 7 6 8. So we have like 2 sentences. We have 1 to 8 each sequence size, like each sentence length, with a real and the padded tokens as well, and each token is represented with the help of this 768 values, okay, as it's a vector. So we get this, you can say B batch size, and then we have the sequence length, and then we have the dimension. So this is what we are going to pass to the QKV, and we will create 3 different projections. Okay, this is going to be the Q projection, this is going to be the K, and this is going to be the V. They will have same shapes. Okay, so B sequence length and dimension. Okay, so what actually we want to do here, we want to create 3 different projections. So for each token, we want to have this query vector. Okay, so let's say this is our query. Okay, in this query we will have this kind of matrix. Okay, and it will have rows from 0 to 1 to 7. Okay, so this is Q. Okay, so it means the query of uh, 0th token is going to be in this 0th row, and each row, like each token, is going to be represented with 7670 to 767. So it means it will have 768. Okay, and yeah, this is for query. Okay, same goes for K. Okay, so this is for the K here. Okay, 0 to 1 to 7, 0 to 767. Okay, this is K, and then we have same for the value. Okay, so we are going to have these 3 projections. Okay, again 0 to 1 to 7, 0 to 767. Okay, so each token has this query vector. Okay, all these 128 tokens in the sequence, and all the tokens also going to have this K, the key vectors, and also all the tokens are going to get this value. Okay, now intuitively speaking, this query is something that asks the question, like the query of each token is going to talk to the key of each and every token in the sequence. It will ask each token's key how much similarity do we have. It will give us the weightage, and then after that weightage we will add what can I offer, that is coming from the V, is going to be weighted with this QK dot product. Okay, so if you just look into this QKT, okay, so we are going to take the transpose of this, and we're going to multiply it with this. In this case, let's say if we have 128 and 768, this is the shape of Q. And if we look into this 128, 768, so we are going to multiply on these 2 dimensions. Okay, so how it is going to work, we are going to have a simple mathematics rule. Okay, so we want to have a transpose of K, that is why we have this K transpose. Okay, so if you just transpose it, so we will have 768, and here we will have 768 128, and the result will be 2 128 128. So these two matches. Okay, so this is going to be the result. So we will have a resultant matrix of 2 1 to 8 1 to 8. Okay, so to do this, I'll just, okay, so this is this very first step. Okay, matmul of the q and k, you can see. Okay, I'm just going to come here. Okay, and here I'll simply in this forward, I'll store the result in scores, and this scores is going to be equal to torch.matmul. Okay, and inside this I am going to pass q and k dot transpose. Okay, and here I will just pass the last two dimensions. So I'm going to transpose on the last two dimensions, so -2 and -1. Okay, and this will give me the transpose of k, and the result we are going to store in the scores. Okay, now the next step is we are going to divide these scores with the dimension of k. Now, why we do this? When we multiply these matrices for larger dimensions, we keep on adding the values. Okay, so like the row of first, like this query with the k. So if we have more values in it, so we will have like r1 c1 plus r2 c2 plus, so if we have more values, we'll have a larger value, okay, as a sum. So with these larger values, then if we pass it to the softmax, it could be a key softmax result, where the weightage will be given to the one dimension maybe, okay, all the probabilities, and the other probabilities are going to be near to zero. Okay, but we do not want that behavior, that near to zero values. We will have the vanishing kind of issues. What we want to do, we want to just scale these values with dk. dk is nothing but the dimension of k. Okay, and here we have same dimension for qk. Okay, so if I just write here self dot dimension, self dot dimension is going to be equal to this dimension. Okay, so I'll just simply use this, okay, scores, and I'll divide these scores with the okay, let me also import maths over here. Okay, math. Okay, and this math is going to give me the square root, math.sqrt square root. Okay, and this square root we are going to use then, and here we will pass the self dot dimension. Yes, and it will give me the scaled values. Okay, so now we are done with these two stages, okay, like matrix multiplication of qk, and then this scaling part. Okay, before applying the softmax in the attention mechanism, we apply this masking. Okay, why it is important? If I recall this to you, so we have some, let's say, CLS token. Okay, then we have I like this. So let's say we have these real tokens. Okay, and then this SEP. Okay, these tokens, we get these tokens from the tokenizer, and also if we paired it to the maximum length, what we get some extra values over here. I'll just write them with red. Okay, so these are nothing but the padded tokens. Okay, and the tokenizer will add these padded tokens till the 128 maximum length. Okay, so this is what we are going to get. Okay, so if you notice in this now, we have these real tokens 1, 2, 3, 4, 5. So this attention mask will be something like it will be the a list of binary values like 0 or 1. So for each real token it will have 1, 3, 4, 5, and for all the padded tokens it will have 0. Okay, so it basically helps us in identifying these padded tokens. Okay, because these padded tokens were not in the original input. We added these padded tokens to match the maximum input size. Okay, so this attention mask, I'll take this attention mask and I'll apply this on the attention scores. Okay, so once I get the results from this 2, 1 to 8, 1 to 8, so these are nothing but, you can say, if I just consider here 1. Okay, so it is 128 by 128. Okay, 0 to 127, 0 to 127. Okay, so this each row is basically the query. Okay, so we will have, let's say, the zeroth zeroth token here and the zeroth token here. So at each intersection we will have here, like at 0, 0, we will have the attention scores that we got with the multiplication of q with k, query of token 0 with the key of token 0. Okay, so we got this value. Similarly, we got this query of token 0 with the k of token 1, so we got the next value. Okay, so this first row is basically the scores of 0 token with all the keys of the remaining tokens in the sequence. Okay, if you notice here, down column wise like this, we have all the keys. Okay, and so these keys basically we want to, now if you look into first this 0th token key, then the first token key, then the second token key, then the third token key. So in real we had 5 tokens, let's say. Okay, so we will apply this attention mask to identify the real keys. Okay, and also the padded keys. Okay, why? Because we only want our query vectors to attend to the real key vectors. That is where we apply this masking, and every padded token key, like starting from this point maybe till end, we will just make these values, let's say, minus infinity. Okay, and when we will pass this through the softmax, so this softmax will make it 0. That is what we are going to perform with this masking now. Okay, so we have already passed this attention mask. Okay, and we have now this scaled value. We will now perform the masking, and then we will apply the softmax. Okay, so if I show you this now here, how we are going to do this, this is our attention mask. Okay, this attention mask is now, I am going to just call it the maybe the extended attention mask. It is going to be equal to scores. Okay, and in this scores I'll just masked fill. Yes, this masked fill, and in this the attention mask, this wherever this attention mask is equal to 0, I'm going to assign this minus infinity, I guess. Yes, this is the one. Okay, so what this extended attention mask is going to do, it will apply this attention mask on this, okay, and it will just zero all these values. But there is one issue, I can see it, okay, and that is, if I show you, first of all, let me just comment this down and return these scores, okay, and yeah, just execute this, and then is not defined. How is it possible? Okay, so I think I need to execute this. But first I need to execute this, then this, and this. Okay, I want to just execute all of these above parts. Okay, here this I am going to copy this, okay, and I'll just paste it over here. But before this, I just want to execute this, okay. So now I'll just copy this, okay. Now I am basically having these two sentences. Let me just make it one, okay, and here I'll just take this to the tokenizer will give me the input values. I will just also extract the attention mask, okay, we have already discussed all this. So from the out, I am going to extract the attention mask, and then here I am just going to create the embedding object. So embedding object is going to be equal to embeddings, and here I will just pass the embedding object the input IDs, okay. It will give me the input embeddings, okay, input embeddings, okay. And once if I execute this, I can see the input embedding dot shape, okay. Yeah, it is the output of the embedding layer. Now I'll just make this attention object, and it is going to be equal to the attention head class, okay, attention head class, okay. This is going to get just the, okay, here I will just pass the input embeddings and attention mask, okay. So if I just pass the input embedding and also the attention mask, okay, and I'll simply just, okay, this is not where I'm going to pass it, just creating the object here. I'll just pass it, okay, attention object, and here I'll just pass these two, and I'll store the result, okay. And in result I want to see the scores, okay. So scores are going to be the output, and then I'll just print the scores, okay, dot shape. If I just show you, this is 128 128, okay, the same size that we discussed over here, 128 128. So doing great. And also if I just print the attention mask dot shape, okay, so this is the issue. This is not matching to this. So what I'll do, I'll just add extra dimension right here. So for that, I will just quickly, before doing this, I will just make this attention. Okay, and attention mask, I'll update it. How I am going to update it? I am going to update it with attention mask and just simply all the batches, and here I'll just add another uh, dimension, none, and then all the values. Okay, if I now return the attention underscore mask, okay, and yeah, in the scores I will be getting the attention mask. Okay, so whatever I get as a shape, it means I'm getting the shape of the attention mask. Okay, so if I pass it, it is 128, and if I print it here, it is 128. Okay, so it will then stretch this dimension, okay, like broadcast it, and then I will just apply this last dimension on the keys of the tokens. Okay, so this, if I apply now, okay, it will give me the it will give me the, let me check this. Okay, so it will give me the values of, so I can call it the attention, or you can say the masked score. Okay, and I'll just comment this down. I'll just return the masked score. Okay, and I'll execute this. Okay, and I'll now execute. Before I execute this, I'll just print it. Okay, and this is what I'm going to get. Yeah, I think we are doing great. We are adding it. Okay, so yeah, that is all before passing it to the softmax. Okay, so next I'm going to uh, call it weights, and weights are going to be equal to the, let's say, uh, torch dot uh, softmax. Okay, in this I will be passing the masked score. Okay, and this masked score, I'll apply this softmax on dimension 1. Okay, so each row will have the probability sum to 1. Okay, and yeah, this is going to be the weights. Okay, and yeah, I guess it's done. So if we just open this, we can see we have applied this and this softmax as well. Now we have this output ready here, and we'll multiply this v now with the output of the softmax function. So if I just show you weights, I'll be returning these weights, like the final weights after the softmax. Okay, and you can see in the scores I am now getting the weight. Okay, so each scores now, they basically have probabilities sum to 1. Okay, and that the zeros we get because we added infinity, like negative infinity, to the padded keys, and we are now getting this. Okay, we are going to now perform the let's call it context, and this context is now going to be equal to matrix multiplication of the weight. Okay, let's call it weights. Yes, so weights and v. Okay, and now we will return this context. Okay, and with this context now I think we will get our here I'll just call it context to avoid the confusion. Okay, and if I just print the shape, okay, why are we getting this? Okay, so we are still calling the scores. It must be 128 by 767. Okay, 768. Okay, so yes, this is the. So why? Because we just multiplied these two, like this value of 128 times 128, we multiplied it with the v, when v is 128 768. Okay, so if you multiply this, okay, on these internal dimension, they are equal, so we will get this result. So the result is going to be 128 768. Now this is the output. So with this, now you can see we have this attention scores. Now the input has the contextual awareness. Okay, this is what I wanted to show you for this video. Okay, now in next video we are going to split this, okay, into multiple heads. So this is the just one head. In next video we are going to split the same single head into 12 heads. Okay, and each head will be performing its own task, like it will be getting a slice of dimension from the 768. Okay, that depends upon the number of heads, how many dimensions are we are passing to each head, and then each head will perform its part, and by the end we will concatenate them. So we will take the same scale, dot product attention, we will just create these heads, and by the end we are going to concatenate them. Okay, so this is all about this video. I hope you enjoyed the lecture. I see you in the next lecture.